Hello everyone, and welcome to section 4.1. We'll also do section 4.2 and 4.3 in this video. So again, not here on Monday, so this video will make up for that day. We don't want to lose another one. We just lost the day for Labor Day. Well, not lost the day, we had a day off, but I don't want to fall behind. So in this video, I'm going to focus on these three sections because they're very related as far as solving systems of linear equations. It's just different techniques. So each section, 4.1, 4.2, and 4.3, talk about the same concept overall, but just using different techniques to solve those problems. So starting with 4.1, we want to talk about systems of linear equations. Now, we've already solved the linear equations, but we haven't seen a system of equations where we have to solve more than one linear equation at the same time and satisfy both. So a system of linear equations looks like two equations that are linear and it could be written out so, and here I have them in standard form, and this is what we would call a 2-by-2 system. And that is to say that there are two equations. In total, we have two equations. And we also have two unknowns. All right, so these are our unknown quantities. A, B, C, D, E, F, those are just numbers for us. All right, so two equations, two unknowns. We call that a 2-by-2 system. And that's all we're going to focus on. You can have systems where you have 3 equations and 3 unknowns, or maybe you have 5 equations and only 2 unknowns, or you have 2 equations but 6 unknowns. It can come in a mixed bag depending on what you are given, but we are going to specifically focus on what we call 2-by-2 systems, 2 equations and 2 unknowns, x and y. And what we want to do is look at these two linear equations and see if there is a very specific set x and y that solves both of these equations at the same time. We don't just ignore one equation and try and solve the other. We want to make sure that we are satisfying both equations at the same time. So what might work in one equation might not work as a solution in the other equation. We want equality for both at the same time. Now, since these are both linear equations within the system, they are just straight lines. So one way that we can look at them in terms of trying to find a solution is by graphing. If we graph the system of linear equations, we're just basically graphing two lines, right? We can solve for y, put it in y equals mx plus b, graph it. Same thing with equation 2, solve for y, graph it. And we can see different situations. They may intersect, they might be perpendicular, they might be parallel lines, they might be the same line, one on top of the other. So there's lots of different situations that we can come across, and we just want to be able to identify those different types of situations. So here are the types of solutions that we might see. For systems of linear equations. And again, we're just sticking to 2-by-2. So first situation we might see when we look at a linear equation and graph it, call this equation 1. Compare it with a second linear equation when we graph it, call that equation 2. we can find a point where these two linear equations intersect on our xy coordinate system, then this pair x1, y1, whatever those values are, whatever this x value is, whatever this y value is, that ordered pair becomes the right x unknown that we need and the right y unknown that we need to solve this system. So this would be our solution to the system of equations. And notice it would be a very specific solution. It would just be that one ordered pair. So when we get that, we get a very unique solution that is great, that is awesome, because we've solved the system. We've chosen the correct x value and the correct y value. That simultaneously is on the red line and the blue line at the same time. That means we solved the system, but that doesn't always happen. Sometimes we may graph our first linear equation and then graph our second linear equation. And in this case, these two lines are parallel, meaning that they will never intersect, meaning that there is no ordered pair that solves one while simultaneously solving the other. These solutions need to solve both at the same time. Any point I pick on the blue line will never be on the red line, and vice versa. Any point I pick on the red line will never be on the blue line. So I will never get an ordered pair that is simultaneously on both of those lines. So in this case, we would have no solution. There would be no solution to our system because, unfortunately, no matter what x and y ordered pair I choose, it will never satisfy both at the same time. And another situation that can happen, when we look at first equation being graphed, and then we find the second equation, graph its line. This one's always hard to draw because realistically, when we graph them both, they are the exact same line, meaning that they just overlap. So I get this line, and when they overlap, in this case, every point on the first line is also on the second line. This is a case where we would have infinitely many solutions. They're the same line. So we have infinitely many solutions. Try not to write too far over there. But no matter what point I pick, it's on the first one, it's also on the second one. It's on the first one, well, it's also on the second one. Doesn't matter where I go on the first line, I'm also on the second line. Obviously, the best situation for us would be to get a nice unique solution. But those other two situations can happen. When there's no solution, we just say, like we said before, no solution, and we just move on to the next problem. But when there are infinitely many solutions, the only way to write those solutions out is by using a set, and I'll show you how to do that when we get to an example where we have infinitely many solutions. But for right now, let's just keep that in the back of our mind. That these are the three types of situations that can happen when we solve a system of equations, of linear equations. So this is what we're going to focus on, solving two linear equations at the same time and satisfying both. 4.1 has us doing it using this graphing technique, which is actually really not the best way to solve a system of linear equations because it involves a lot of drawing and then using your eyeball to make sure you find the right point. 4.2 and 4.3 will introduce some other techniques that will have us do a little more algebra in order to come up with a solution, so we don't have to keep graphing things. So let me show you an example where we want to have a system and a couple proposed solutions and check and see if it really is a solution or not to the system. So determine whether each ordered pair is a solution to the system of linear equations. So right off the bat, they're just going to say, hey, here's a system, and we think these might be the solutions. Can you check for us? That's what we'll do. X plus y is equal to 8 is our first equation. 3x plus 2y is equal to 21 is our second equation. And we draw the system, we draw this like little squiggly brace on the left-hand side just to denote that we're separating these two equations, but they are related somehow within the system. So there's our system. Our first proposed solution, we don't know if it works or not, is 2, 4. The second proposed solution is 5, 3. And the third proposed solution is 0, 0. So we've got a system with a spot for our x and our y values. Remember that in ordered pairs, the x value always comes first, the y value always comes second. So what we're doing is just checking. That's all we want to do. All we want to do is just check to see if these are going to work within the system. So it's a very specific system, and it asks us that x is 2, y is 4. And same thing in the second equation, it asks us what happens when x is 2 and y is 4. Now, right off the bat, when we check to see if this is a solution and does work, the first equation gives us 6 equals 8, which is wrong. I don't even have to check the second one because it needs to solve both. It doesn't even solve the first one. Right? If I check the second one, I'll get 6 plus 8 again. If I do 8 plus 6, it's telling me 14 is 21. Still wrong. Right? But what's happening is we want to say that this 2, 4 is not a solution. What that means is that if I graph either of these lines, that point is not on either of those lines. There's no way, right? Because I'm getting a false statement. This point needs to be on that line to maintain equality. And I'm not maintaining equality, so this point is not on the line. It's not a solution. Let's check the second one and see if it works. So now we're taking the ordered pair 5, 3, and what we're doing is we're replacing x with 5 and y with 3. Same thing in the second equation, replacing x with 5 and y with 3. And seeing if we can declare this as a solution. Well, 5 plus 3 is 8. So it works in the first one, but that doesn't mean it's a solution to the second one. We know it's a solution to the first one, good. We still have to check the second one. It has to solve both. Well, 3 times 5 is 15, plus 6 is 21. Well, yeah, 15 plus 6 is 21, so we're good. It solves both at the same time. Therefore, 5, 3 is a solution. That means that the point 5, 3, that ordered pair, that is a point that is both on the first line and the second line. So they're crossing and they just happen to cross at that point because that point is on both of those lines. So that's our unique solution. And for the last one, again, that one's kind of silly. Right? It's having us plug in 0 for x and 0 for y to see if it equals 8 in the first one. Again, I don't have to go any further than this. 0 does not equal 8. This is wrong. So So this is not a solution. All right, if it doesn't work for one, there's no way it's going to work for both of them. It didn't even work for the first one. It'll never work for both of them. All right, so here they're giving us some solutions, but mostly our job is going to be finding those solutions. They'll just give us the system, and we have to find the solutions. They're not going to give us a list, and we don't want to go down an infinite list of ordered pairs and try them all. We want to be able to just look at a 2x2 system and do a little solving and pluck out the actual solution that we want. So again, 4.1, the first technique is going to be using graphing. So we want to solve the system of linear equations by graphing. So we have our graphing skills for graphing an equation. Now all we have to do is just graph two equations. So we're just going to do the exact same thing we did before with the graphing, but we're just going to graph two on the same graph. So let's pick up a system x plus y is equal to 3 and x minus y is equal to 5. Again, they give us a system, and it is our job to find the solution. That solution now, again, we need an x and we need a y. Right? So our solution isn't just one number like x equals this. Our solution is an ordered pair, a very specific ordered pair of this x and this y. So don't get those mixed up, because ordered pairs always come in an order, right? That's why they call them ordered pairs. So first things first, just to make the graphing easier, I'm going to rewrite these in terms of y equals mx plus b, so that I can look at my y-intercept and then count out my slope. It's just the nicest way to graph these. And I'm going to put them in that nice order. This one right now, be careful because it's negative y is negative x plus 5. That's not y equals mx plus b. It's not solved for y. So I'm going to multiply the left and the right by another negative in order to get that negative on the left-hand side to cancel out, so that I do have y equals negative x plus 3 and y equals x, because negative times negative is positive, minus 5, because I'm distributing that negative. So these are the two linear equations that I want to graph. Now, one downfall to this method is, if you don't have graphing paper, you have something like this where it's just plain white here. If your scale is off, then your lines might be a little slanted or crooked. It might be hard to really visualize that point that is the solution. So you want to be careful and try and maintain a nice scale here. I do have to go all the way down to negative 5. So I'm going to do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So again, if like one of your scales is a little off, it's squished or it's extended, then your line's going to like get squished or extended. And it would be hard to pick up that point where we have a solution. So let's see what we get. I'm going to start at 3 on the y-axis, and I'll call this equation 1. I'll do it in blue. So let's start at positive 3 on the y-axis and count out our slope. It's negative 1. So that means my slope goes down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. Notice I keep counting because I want to try and draw as much of the line as possible, and I want to be pretty consistent as to where that line goes. I don't want to say down 1 over 1 and then just really quickly draw a line out that way, because if the line doesn't go out that way, it goes down this way, then I might mess up where these two lines intersect. Again, you can see there's a downfall to using graphing to do this. It's taking quite a while. And if I don't graph it precisely, my graph could lead me astray. Second equation, y equals x minus 5. I start at negative 5. There's my y-intercept. This has a slope of positive 1, so I'm going to go up 1 and to the right 1, up 1 and to the right 1. Right? Every time I do that, I land back on the line. Up 1 and to the right 1, up 1 to the right 1. So now I can identify that as I counted out my slope down here, I got to this point 4, negative 1 on the first line. And on the second line, when I counted my positive slope up and over, I got to this point 4, negative 1. That's also on the second line. So when I look at both of these lines, they both share the same ordered pair, and that is the ordered pair 4, negative 1. So that is my solution. That point 4, negative 1, that ordered pair very specifically solves my system of equations because it works for both at the same time. So let's go ahead and do another one. Again, we're leaning on that graphing technique in order to pick up that point where they intersect, if they intersect. Sometimes they might not intersect at all. So the next one is x minus y is equal to 4 for the first equation, and x minus y is equal to 1 for the second equation. So here is a 2x2 system, 2 equations, 2 unknowns. Let's solve it by graphing. Again, the best way to graph is to solve for y, use that slope, use that y-intercept. So I'm going to subtract x on both sides, and I'm going to do it for the second equation as well while I'm at it, so that I can get negative y is negative x plus 4. And again, look at the order that I'm putting them in. The negative x plus 1 for the second equation. I'm putting in y equals mx plus b, so I'm putting the x part first and the b part second. If you swap those around, you might trick your brain into thinking the slope's 4 or something like that. It's not. The y-intercept's 4. That's why you want to write that constant all the way on the end. Still not in y equals mx plus b. I've got to be careful. You know, my slopes aren't negative 1 because I'm not solved for y. So I've got to look at this in terms of a y equals. So I'm going to multiply both sides by a negative in both equations. And that will just rewrite my system as y equals x minus 4 for the first equation, y equals x minus 1 for the second equation. So these are what we want to graph in order to see if we can pick up some solutions. So again, I have to go on the y-axis as far down as negative 4. 1, 2, 3, 4. 1, 2, 3, 4. A little long. So I'm going to start down at negative 4 on the y-axis. Notice they both have slope of 1, so up 1 over 1, up 1 over 1, up 1 over 1. Again, every time I do that, I'm landing back on the line. And up 1 over 1. That's good enough to get that first line. And then for the second equation, I start at negative 1 on the y-axis. But I have the same slope, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Remember that if you run out of space here, or if you want to work backwards, instead of looking at the slope of 1, which is positive 1 over positive 1, you can do this little trick where instead of doing positive 1 over positive 1, you can go negative 1 over negative 1. That's still a positive 1, down 1 to the left 1. You're working your way backwards, but you're maintaining the proper slope. You're staying on the line. Now, we've already seen this situation before where we had 2 lines with the same slope. We used the definition of parallel lines when we talked about those. And that's exactly what's happening here. These two lines are parallel. They will never intersect. So we've got these two lines that are parallel. Can't find a point where they intersect. No matter what x, y ordered pair I pick on the green line, there's no way it's touching the red line and solving the red line. Vice versa, no matter what ordered pair I pick on the red line, it will never touch the green line, so it won't solve the green line. So anything that solves the first equation is not going to solve the second, so I won't solve the system, and vice versa. So this is a case where we just say there's no solution. Nothing can solve this system. I can solve one equation at a time separately, but I can't find an ordered pair that solves both at the same time. It's just not going to happen. So again, there's our graphing technique. You can see how that can be a little cumbersome because you've got to draw a lot and then you've got to eyeball the solution. There's got to be a more rigorous mathematical way of doing it. And the answer is, of course, yes. And we want to get away from this graphing technique pretty quickly and get into something that's a little more easier to use, because what happens when you start seeing fractions in the system and then you have to start eyeballing where that fraction is. Is it a half? Is it a third? I can't tell based on this space that I'm staring at exactly where that point is. So we want a little bit more rigorous way of solving these equations so that we can pick up the exact number. It might be 7/10 is the x value we're looking for. It's really hard to eyeball 7/10 when there's no hash mark for it. So we'll get away from the graphing and we'll talk about section 4.2, which means we're still solving systems of linear equations, but the technique we're going to use is a technique called substitution. So, don't get me wrong, graphing's nice. It's a good thing to know how to graph, but it really slows us down in terms of solving systems. Because what if a system has 10 equations and 10 unknowns? Do you really want to draw 10 lines all in the same coordinate system? I don't think so. That would be ugh. So let's look at this substitution technique. I'm just going to start with a nice working example where we solve the system by substituting y equals, let's take negative 3x in the second equation into the first equation. Meaning that we're given a system that looks like x plus y is equal to 6, and they tell us y is equal to negative 3x. This is how we go about substituting something in. We know what y is. Y is exactly negative 3x. So we're taking that substitution from the second equation and looking at the first equation and saying, why do I have two different variables in the first equation when I know what y is in terms of x? There's no reason for me to have an x and a y in this first equation when I already have the knowledge of what y is. I can simply rewrite this system by substituting in negative 3x wherever I see y. Right, because I already know that. Now, what that does for us is it has us take this first equation, and notice this equation only has x. X minus 3x is equal to 6. Now I just have one linear equation with one unknown, I can find x. Right? We go back to our old technique of just finding x. We've got 1x minus 3x, that's negative 2x, which is equal to 6. And then I can divide by negative 2 to get x is equal to negative 3. Now be careful. Before, when we were just solving linear equations, we would just stop there and say, hey, this is what x is. Well, remember, we still need to find y. So once we've got our x coordinate, we need our y coordinate, because again, these solutions to 2 by 2 systems, they come as an ordered pair. You need an x value and a y value. Well, the nice thing about the substitution method is I know that y is just negative 3 times x, and I now know what x is. So I know that y is equal to negative 3x, which means y is equal to negative 3 times, well, this is x, negative 3. So y must be positive 9. So there's my solution. It is the ordered pair negative 3, 9. You can either just circle each the x and the y, or you can write it out as the ordered pair negative 3, 9. Just don't write 9, negative 3, because then you're writing the y where the x goes and the x where the y goes. All right, the point 9, negative 3 does not solve this system. The point negative 3, 9 would solve this system. If we were to graph both these equations, we want that ordered pair, not vice versa. So I told you, in that problem what to substitute in. They don't always tell you what to substitute in. You make the choice, really. That's the nice thing about the substitution technique. You get to make the choice. So solve the system of linear equations. Using the substitution technique. Or method, if you want. So, let's take a new system and practice this technique. Again, you have to solve both of these at the same time to pick up the correct x and y value. The first equation they give you is 3x minus 4y is equal to 10. But then they tell you that y is equal to x minus 3 for the second equation. So you've got two equations. Now the substitution technique lends itself very well when a setup is like this, where one of the equations is actually already solved for the other variable. So this is y on the left-hand side of that second equation. So you know what y is. You know what y is in terms of x minus 3. You don't know the numerical value of y that solves it, but you know the expression that y has to satisfy. Y has to be x minus 3. So what we're going to do is substitute that into the first equation where we see y. So we're going to take this expression and plug it into the first equation. That's our substitution. So it was already there waiting for us ready to go. So now that's going to have me solve 3x minus 4 times, and again, this is y, x minus 3 equals 10. Same equation, 3x minus 4y equals 10. Here it is, 3x minus 4y equals 10. But I'm simply rewriting y as it is in the second equation. So that tells me that I really do need to distribute this negative 4 because I'm looking at 3x minus 4 times this expression that has two terms. So let's make sure we go ahead and distribute the negative 4 across there correctly. That will give us 3x minus 4x minus is plus 4 times 3 is 12 equals 10. And again, notice I'm just working with the one equation now. and it's all in terms of x. So after that substitution, you don't have to worry about the system anymore. You're just solving one equation because you only have one variable. So 3x minus 4x, there's a negative x, plus 12 is equal to 10. Let's subtract that 12 on both sides. We get negative x is negative 2, but we don't want to know what negative x is. We want to know what positive x is. It's positive 2. So we'll clean that up by multiplying by a negative on both sides. Negatives cancel each other out. And we've picked up our proper x value. Again, not the final answer because that's only half the solution. Our solution is an ordered pair with x and y. Well, how do I go back and find y now? Again, I just use that substitution. That's the nice thing about the substitution technique. You know y has to obey this x minus 3 expression. And you know x is 2, so you're just going to plug that in to figure out that y has to be negative 1. Combine these two together, write them as an ordered pair, and we'll have our solution 2, negative 1. That's our solution. So we do get a nice unique solution. These two lines do intersect. They intersect at the point 2, negative 1. Let's go ahead and do another one. Let's say we have a system that looks like 3y minus x is equal to 6, and 4x plus 12y is equal to 0. So again, we want to do this with our substitution technique. Now be careful because explicitly x or y is not really solved for in this case. We have to do a little bit of work to choose, and this is where you have some choice. So you can pick which variable you want to choose in order to make a substitution. I am going to make the choice that in the first one, I want to solve for x equals everything else. So the way I'm going to do that is I'm going to take this first equation and I'm going to add x to both sides so that I can get the x over on the right-hand side here. And I'm going to subtract 6 on both sides so that I can get the 6 out of the way on the right-hand side. That will generate 3y minus 6 is equal to x for the first equation. The second equation I have not touched. It's still 4x plus 12y equals 0. Now I have a situation where x is exactly this value, 3y minus 6. I know what x is in terms of y, so I'm going to go to my second equation and replace this as my substitution. That way I'll have 4 times 3y minus 6 plus 12y. That'll all be in terms of y. Then I only have to work with the second equation. Then I only have to worry about 4 times the quantity 3y minus 6, because that's exactly what x is. I'm just simply making that replacement. So I'm substituting x in for its expression, 3y minus 6. Don't forget the plus 12y, and that equals 0. So here, we do that one in blue there to be consistent. So I still have the exact same second equation, but I have it written out so that x has been replaced with the y expression, 3y minus 6. This is just one equation with one unknown variable. Let's find that variable. So So again, I'm going to distribute the 4 to get 12y minus 24 plus 12y is equal to 0. Both of these are positive 12y. So I've got 24y minus 24 is equal to 0. Let's add that 24 over on both sides so that we get 24y is equal to 24. Let's divide by 24 on both sides. 24 over 24 is exactly 1. So then my y value must be exactly 1. Now this time we found y first, and the reason is because we chose to substitute x equals this expression for y in, which gave us an equation with just y. So we found y first, but that's still the second coordinate for the ordered pair, so keep that in mind. Again, how do we go back and find x now? Well, we knew that 3y minus 6 was exactly x, meaning that we just plug that y value right in because we know y has to be 1, and x has to be this expression in terms of y equals 1 plugged in. So we get 3 minus 6 is x. So we get negative 3 for x. That means that our solution is going to be the ordered pair. Again, careful, the x coordinate always goes first. So it's going to be the ordered pair negative 3, comma, 1. That is the point where these two linear equations will intersect, meaning that that ordered pair simultaneously solves both those equations. Thus is our solution to the system. And we'll do another one. Something funny might happen with this one, fair warning. Here's our system. 2y is equal to x plus 2, and 6x minus 12y is equal to 0. So again, we want to try and use this substitution method. If I look at this and try and pick something to solve for so that I can then make a substitution, if I say in the first equation, oh, I want to solve for y, and I divide by 2 on the left and the right, notice I'll generate a fraction in front of the x. That might not be the best way to go with it. Maybe in this term, or maybe in this case, you might want to solve for x by just subtracting 2 on both sides. That way you get x is 2y minus 2. And there's no fractions. With practice, you'll be able to see, what the best thing to solve for is. In this case, again, like we did in the last one, I'm going to solve for x equals some expression in terms of y. And I'll do that by simply subtracting 2 on both sides. So we'll rewrite the system. 2y minus 2 is exactly x. The second equation is still 6x minus 12y equals 0. Now, x is this expression, 2y minus 2. And x in the other equation is sitting right here after this multiple of 6. So let's go ahead and substitute that into the second equation. That way we only have to work with the second equation by saying that 6 times 2y minus 2 minus 12y must equal 0. So again, I've made that substitution for x. There's my substitution for x, sitting right where x used to be. And I have an equation that only has one variable, y. So let's solve for y. Distribute to give us 12y minus 12 minus 12y equals 0. Well, now we have positive 12y and negative 12y. Those cancel out, and I get negative 12 is equal to 0. Now this is false. We used to see this happen before when we solved linear equations. Whenever we got some nonsense like this, negative 12 equals 0, no it doesn't, we would say that there is no solution. And the same thing is happening with this. This system of equations has no solution whatsoever. So that is our final answer. There is none. We can't find a solution to this system. So in fact, when we see this situation happen, there's no solution. Remember what that looked like graphically when we looked at something like this that had no solution. We had two parallel lines. So that must be the case here. These two lines, if I were to solve for y and put them on a graph, I would get parallel lines because they don't intersect. I can't find a point that is on both lines simultaneously. So that's the situation we're in here. This system, this gave us two linear equations that, those happen to be parallel lines. That's why we were unable to find a solution. Let's see, let's do one more from this section. Make sure we've got it. And I'm going to pick on this one because it has a nice fraction in it. 1/3 x minus y is equal to 2, and x minus 3y is equal to 6. So again, you have some choice. What do you want to solve for? In this case, let's solve for, let's say we want to solve for this x in the second equation by adding 3y to both sides. Is that the only choice you can make? No. You could solve for y in the first equation, add y, and then subtract 2 on both sides. You could have y solved for in the first equation. There's nothing stopping you. You could multiply the entire first equation by 3 to cancel out that fraction. Right? There's nothing stopping you from doing that. As long as you maintain the equality by doing the same thing on both sides, you're never changing the system. Right, so I'm doing the same thing on both sides here, so I'm not changing the system. I'm simply rewriting it so that I can see a substitution, and in this case it'll be x equals 6 plus 3y, or 3y plus 6 if you write it the other way. All right, so I have not changed the system. It's the exact same system. I just have it written a little differently so that I can clearly see my substitution. It tells me that wherever I see x in the first equation, I'm going to write 6 plus 3y. Well, that's where I see x in the first equation, so that's where I'm going to write 6 plus 3y. So I'm multiplying 1/3 by the quantity x, which is 6 plus 3y. Then I'm subtracting y, then I equal 2. So there's the first equation rewritten with x replaced with its substitution, 6 plus 3y. Now I have an equation that only has y. Let's solve for y. I'll have to multiply 1/3 times 6. Well, 6 divided by 3 is just 2. And 1/3 times a positive 3y. Well, times 3 and dividing by 3 just cancel out, so I get my y. And then I subtract y, and I set it equal to 2. So cleaning up that left-hand side, I get 2y minus y equals, 2 plus y minus y is equal to 2. Positive y and negative y cancel each other out. And I'm left with this expression, 2 equals 2. Well, yeah, 2 always equals 2. So this is a case where we would have infinitely many solutions. But what we don't want to say is all real numbers, because we're not talking about a number anymore. We're talking about an ordered pair. They're two specific numbers that have to be related to each other. When we see this case of infinitely many solutions, that means that our two lines, when we look at our two lines, they actually are one and the same. Right? They overlap each other so that all the points on the first line are the same as all the points on the second line. So by doing that, we don't want to say all real numbers, because then you might run the risk of saying, oh, well, the ordered pair 0, 0 is a solution. No, it's not. It's not on those lines. So you can't just pick any two real numbers you feel like picking, because you might land at a point somewhere way off in space that is nowhere near these two lines. And in fact, these two lines are the same line. They're just written a little differently so that they hide the information. But they are the same line. They have the same slope and they go through the same point on the y-axis. So if you just pick a random point out in space and say, hey, those two real numbers work, no, they don't. They don't work. They have to be on the line. So when you write out the solutions for this, the solutions are going to come in a set. Yes, there are infinitely many of them, but they have a certain rule that they have to obey. And what that rule is that you can let y be any number you want. Look at your substitution. I could plug any number in I want for y. Say I plug in 0, then x is 6. See how it generates the next value? If y is 1, then I get 6 plus 3, which is 9, and x is 9. If y is 1, x is 9. Right? So I can't just pick two random real numbers. I have to let one of them be any number I want, and it generates the other coordinate of the ordered pair. So go back to your substitution, and you can generate that missing value. In this case, x can be generated later based on me just choosing a random y. So I'm going to say that y is any real number. And since we're solving a system, this is why we have to be a little more particular here. X is equal to 6 plus 3y. Right, so y is any number you choose. If you choose any y value, I can go find the proper x value. You can't just choose any y value and any x value. If you pick any y value, there is a very specific x value that goes along with that y value. So we have to write it out as a set like this. And we saw that set notation with the curly braces when we talked about functions. So that's what we're doing. We're just declaring this set. Pick any y. I'll plug it into that expression and find x. So when it comes to when it comes to systems of equations, yes, this is a situation that can happen, but no, we don't say all real numbers, because we're not just talking about one variable x. We're talking about two variables, x and y, that are very specifically related in a certain way. So we have to declare that certain relation, and that certain relation is the substitution, right? So that is solving systems, 2x2 systems, using the substitution method, which can be extended to larger systems. You'll tackle that in college algebra and beyond. But there's one other technique that we need to cover, which gets us into section 4.3 now. So section 4.1, we did some graphing. Section 4.2 looked at substitution technique. Now we're going to solve systems in 4.3 using the addition method. Some people like to call this the elimination method. Number 153. Good there. So again, let's take a working example here. Let's say we want to solve the system of linear equations by, I'm going to get that out of there, adding equations 1 and 2. So here's our system. 3x plus y is equal to 5 for the first equation, and 6x minus y is equal to 4 for the second equation. So we've got equation 1 will be this first equation, obviously, and equation 2 will clearly be that second equation. What they want us to do is use this new method called the addition method. This is also why they call it the elimination method. You are going to be adding these two equations together. But when you add, you have to add like terms. So make sure everything's like lined up in the proper columns so that you add like terms. So when I add these two equations together, equation 1 and equation 2, 3x plus 6x gives me 9x. Positive y minus y just cancel each other out, so there's no more y's. You can see now why they call it the elimination method. I've eliminated y. And then on the right-hand side, if I add the left-hand side together, then I have to add the right-hand side together. 5 plus 4 is 9. What I have done is I have generated a brand new equation based on all of the information within the system. So all the information in this system has now been compressed down into one new equation. And we got lucky that the y's canceled out and that our new equation only has one variable. So I'm staring at 9x equals 9, which means that x is equal to 1. And you see how quickly I pick up that first part of my solution. Again, the solution is an ordered pair, so we still have to go back and find y. But it does give me that first part of my solution. So I added these two together and got a nice equation with one variable. I solved that one variable. This must be the x that solves my system. Now we need to go find y. We don't have a substitution to fall back on where we can just plug that x in and it'll spit out our y. So what we can do is just choose either of these equations. I think I'll choose equation 1. You could put it in equation 2, you'll get the same value. But I'm going to choose equation 1 and plug my x value into equation 1. Because 3x plus y has to equal 5, and x has to be 1, so I'm going to plug that in and say that 3 times 1 plus y is equal to 5. See, again, I've generated an equation that just has one variable y, which is the variable I'm missing. So 3 plus y must be 5. We'll subtract 3 on both sides, and we'll see that y has to be positive 2. Bringing these two things together, our solution must be the ordered pair 1, 2. Again, make sure you put them in order. X value first in the ordered pair, y value second in the ordered pair. Now, they're not all designed so nicely that something will always cancel out right in the first step. This is just a nice first example. So we'll do a couple more examples so we can see how to manipulate these to get that cancellation to happen. You might have to do a couple more steps up front in order to get that cancellation to happen right off the bat before we can move forward. The last thing we want to do is add two equations with x and y together and get a brand new equation that still has x and y. we haven't eliminated anything, and then we are stuck because we still have two unknowns. So let's pick on one where they give us two linear equations. First one is 4x plus y is equal to negative 13. And the second one is 6x minus 3y is equal to negative 15. Now again, if I just add right off the bat equation 1 and equation 2, I'm going to get 10x minus 2y, and that's not going to eliminate anything. So I'm not really set to add these together right now. But it doesn't mean I can't use the elimination method. It just means I have to fix things a little bit first before I add these together. Now, if I take that first equation and I multiply both sides by 3, I could generate 3y to cancel out with negative 3y. So much like with the substitution method, you have a choice to make. Right? I can't tell you exactly the step you need to make. You need to make that choice as to what you want to cancel. I'm choosing to cancel out the y's because I think it's pretty easy to multiply the left and the right of the first equation by 3. Again, not changing the system because I'm keeping the equality. I'm just rewriting the system in terms of 12x plus 3y is equal to, this is still negative 39 after I multiply by 3. Notice I haven't touched the second equation because I want to keep that negative 3y where it is so I can get some things to cancel out. Now, if I set up my addition, I'll add 3y and I'll subtract 3y when I do that addition, so I'll get everything to cancel out. So let's go ahead and add the x's. 18x, 3y's cancel out. These are both negative, so I'm going to get an even much larger negative. Negative 54 when I add negative 39 and negative 15. So let's take a look at dividing this. Since I only have x, should get x is negative 3, all said and done. So 18 times 3 is 54. 54 divided by 18 should be 3. Don't forget the negative, though. Now I need the other part of my answer. And again, there's no substitution to really fall back on. But I'm going to choose one of these equations. And again, I'm just going to choose equation 1. Why? Because maybe the numbers are a little smaller. And I'm going back to before I even did the multiplication. I'm choosing 4x plus y is equal to negative 13. Right, so I'm going back and I'm choosing equation 1. And since I've already found what x needs to be, I'm plugging in that x value. So this is how we'll find y, by saying 4 times negative 3 plus y must be negative 13. So negative 12 plus y is negative 13. And then we'll add 12 to both sides. So that y must be negative 1. So our solution must be the ordered pair negative 3, negative 1. So again, nothing was going to cancel immediately. So I had to tweak it and I had to make a little fix here. I chose to cancel the y's out because I think it's pretty easy to just triple this value to get positive 3y minus 3y. But I can't do it to just one piece. I will completely lose equality and my system goes in the garbage. So I have to maintain the balance and multiply both sides of that first equation by 3 if that's the path I want to take. So again, let's do a couple more. Let's say we want to take about 9x minus 3y equals 12, and 12x minus 4y equals 18. Now, here's something I want to show you, because adding these together won't work. Adding these together won't work, right? You're not going to eliminate x or y. And rather than having to take one of these and, notice they're both positive and these are both negative. If I wanted to cancel something out, they'd have to have opposite signs, and so I'd have to multiply one of these equations by the negative. And also, they're not the same coefficient, so the common multiple that I would have to go for with the 3 and the 4 would be a 12. Ugh, I'd have to multiply by like a negative 4 and then a positive 3. You can save yourself some work if you can realize that in the first equation, everything has a common factor of 3 on the left and on the right. I can divide both sides by 3. So what we're looking at in terms of this first equation is 3 times 3x minus y is equal to 3 times 4. So notice there's like an extra multiple of 3 in there. Same thing in the second equation. Every single one of these has a common factor of 2. This is 2 of 6x minus 2y. And this is 2 times 9. So you can look at that first equation and simply divide by 3 on both sides to cancel out that 3. And same thing in the second equation, you can divide by 2 on both sides to simply cancel out that extra multiple of 2. Now this has us deal with a much smaller system. I mean smaller in terms of the coefficients. So it's a little easier to work with these smaller numbers. Now again, if we're doing the addition method or elimination method, right now nothing will cancel. I'll get 9x, I'll get negative 3y, I'll get 13. It's not going to help. What I need to do is tweak this a little bit so that I can get something to cancel. I'm going to look at the y's. What I'm going to do is I'm going to multiply by a negative 2 in the first equation on both sides. Why am I doing that? Because specifically negative 2 times negative y is positive 2y. When I add that to the second equation, positive 2y minus 2y cancels. So I made that choice to cancel the y's out again. Again, that is my choice. You have a choice. You could cancel the x's out. But I like to think that canceling the y's out is a little bit easier in this case. It will give us negative 6x minus minus is a plus 2y. Don't forget to also do it on the right-hand side, negative 8. Second equation remains the same, 6x minus 2y equals 9. Now I can add these two equations together. Negative 6x plus 6x, uh-oh, that's gone. Positive 2y minus 2y, uh-oh, that's gone. There's nothing on the left-hand side. Negative 8 plus 9 is 1. I just said that 0 is equal to 1. Well, we all know that's false. Should I freak out because I got the problem wrong? No, there's no solution. This happens. All right, we've seen this happen before. When we try and solve a system, and we get some false statement like this, provided we've done all the algebra correctly, then we know this false statement provides no solution to the system. Don't worry, we'll do another one. See how much time we're at here. Okay, a little over an hour. This video will be a little shorter than like the full class time would be because there's no like feedback and questions. But I don't want to make this video like 2 hours long, so let's pick on another one, and let's pick on one that maybe just has some fractions in it. Let's pick on I don't know if I like that one. Let me pick another one. Oh, there we go. That's a good one. X over 2 plus y over 8 is equal to 3 for the first equation, and x minus y over 4 is equal to 0. That's our second equation. And so, yeah, it has some fractions in it. But again, the nice thing about systems of equations, they really are just linear equations. You can treat them the same way. If I don't want to look at these fractions, because right now if I add these together, nothing's going to cancel. But maybe I don't want to look at these fractions. Especially in that second one, I can easily multiply by 4 and not create anything really crazy as far as an equation would be. Just be 4x minus y is equal to 0. So I can clear the fraction in that second equation really quickly. I can do the same thing with the first equation, and again, it's not going to be that bad. I really want this 8 to cancel out though, so just multiplying by 2 is not going to be enough because 2 over 8 is still 1/4. I'll still have a fraction. So I need to multiply by that big guy, 8, meaning that I'll have 8x divided by 2. Well, 8 divided by 2 is 4x. And then 8y divided by 8 just leaves y. And then 8 times 3 on the right-hand side is 24. All right, so even with fractions, you can use your same old tricks to get rid of them so you don't have to deal with them. Yes, the numbers got bigger. Yeah, 24 is a big number, but it's not going to scare us. We can work with it, especially now because look at the y's. When I add these two equations together, positive y, negative y, cancel, cancel. The 4x and the 4x don't cancel out. They're 8x. And on the right-hand side, 24 plus 0 is just 24. See, you got a really nice equation. You avoided the fractions very quickly to figure out that the x coordinate for our solution should be 3. Now I have to go back and plug in that x value to figure out what my y value is. Again, remember, this equation 1 that you have right here is the same thing as this equation 1 that you have right here. All the same information is there. It still has that equality. So plugging 3 into here and then clearing the fraction by multiplying by 8 and then figuring out what y is, you've already done that step. You don't need to redo that step. Just plug 3 into this equation so that you can find out that 4x plus y must equal 24. Tells you that when you plug in x equals 3, 4 times 3 plus y must equal 24, which tells you that 12 plus y is 24. Subtract 12 on both sides, and you finally got y must be positive 12. Therefore, we have our solution. That solution being 3, 12. So that's it. As far as the different techniques for solving systems of equations, it might be a bit to digest. You can go back and rewatch the video, or just break it into parts. Study 4.1 and then take a break. Study 4.2, take a break. Study 4.3, take a break. But again, Wednesday when I get back in class, if you have any questions or you want me to do more examples for any of these methods, I will gladly do some more examples. We'll have the time, so I can assume that you all have watched the video and you're at least somewhat comfortable, and then we can kind of just work through a couple examples if we need to clarify. But other than that, again, I will see you on Wednesday, where we'll start working towards the end of that section. We jump around a little bit by going to 4.5 and then jumping to section 9.4. I know it's a little all over the place for the second exam, but that should wrap everything up that we need for the second exam. So when I get back, we'll talk about that as well. But that second exam, if you're interested, if you're curious, and you haven't shut this video off yet, I will mention this again when I get back, but exam 2 is coming up, but we're going to pick the day to be on the 23rd, which is a Wednesday. That way it gives us some time, and I may get into some of the chapter 5 stuff that comes after this, but it won't be on exam 2. But I'll push exam 2 back a little bit to give us a little extra time. So I may start the next chapter early, but it won't be on the test. But we'll talk about that when I get back. Otherwise, hope you guys have a good weekend. And, again, let me know if you have any questions about this material, and let me know your, thoughts and opinions on how this video worked out for you. Like I said, if it's good and it works for a lot of people, I can continue to do this. So thank you very much.